So welcome everyone to the morning ODOT virtual session on the second day. Today's session is session 6, titled Large Hydraulic Infrastructure Projects. We have 2 great presentations, and then I'm helping out with the third, so that should be great. The first one, we'll get right into it to leave time for question and answer at the end. The first presenters are Jeremy Hedden and Katie Hoensheid with Bergmann Associates. They've worked on challenging projects throughout the Midwest. Today they're going to present on one of those challenging projects. Their presentation is titled Allen Creek Berm Opening, an Alternative to Noah's Ark. So Jeremy and Katie, go right ahead. Thanks.
All right, thank you, Jonathan, for that introduction. We are going to be talking about the Allen Creek Berm Opening project today. So we're going to start off with a little bit of some site history. This project is located in Ann Arbor, Michigan, just north of the downtown area. The image on the right shows the Huron River kind of meandering through that north end of town. And on the south side of that river, the white line represents some MDOT-owned railroad tracks. The pink area is a decommissioned DTE energy site, which has some future development planned for some green space and some commercial storefronts. There's a thin green line that follows the kind of the south or west shore of the Huron River, and it crosses over at the Argo Dam, which is that white rectangle just north of our project site location. And then all the red area you see is commercial businesses, and the green area is residential property. So the city of Ann Arbor has seen a lot of development over the recent years. And the problem that we are trying to solve with this project is flooding. So these images come from a parking lot that is just south of those railroad tracks. And as you can see here, the 100-year floodplain, this is the limits of the 100-year floodplain. Some portions of this floodplain get up to 9 to 10 feet deep. And that railroad berm acts as a dam, preventing the runoff from downtown Ann Arbor from reaching the Huron River, which is at the north end of the picture. Another issue that we have worked with at this site is trespassing. These railroad tracks are an MDOT high-speed rail corridor. And the popular border-to-border trail, which is the green line on this sheet, is separated from the downtown area by these railroad tracks. And so many people cross these tracks every day that Google Maps even shows a white line as a trail crossing the tracks illegally. And this is extremely dangerous because it is a high-speed rail corridor. A little bit of our project history is this project originally, the concept was formed in 2007. In 2012, the feasibility study began, which was wrapped up in around 2013. In 2016, the city of Ann Arbor applied and was accepted for a FEMA grant for the design phase of this project. In 2008 or 17, Bergmann was hired with OHM to start the design phase, which wrapped up by the end of 2018. Also in 2018, the city was accepted for a FEMA grant for the construction phase. The project was let or awarded in 2019, and then construction began in 2020, so this past spring, and it should be wrapping up here in the next couple of weeks. So now I'm going to hand the project over to Jeremy to talk a little bit about the design.
Thanks, Katie. Just kind of diving a little bit deeper into some of those issues that Katie highlighted. The project site is located right at the mouth of the Allen Creek. That's where it empties into the Huron River. And Allen Creek itself was enclosed many years ago, about 100 years ago, and it serves about 5.5 square miles of watershed area. And essentially what we'll kind of show here in the next couple of slides is it's completely undersized. It's handling about a 2-year storm event before it reaches its capacity, and that's contributing largely to some flooding in the surrounding area. So here's kind of an idea of what we're dealing with, a then and now image. So that purple area is essentially the watershed for this Allen Creek enclosure. within the city. And then I kind of overlaid with that an old historic map that I found online, and you can really see how that population center has really grown over time, and essentially the entire watershed is all developed today, and that has contributed to this Allen Creek enclosure being undersized, dramatically undersized. So this project was set up to primarily convey some of this local flooding underneath the railroad tracks and to the Huron River. And that's indicated by a couple of pair of box culverts that you can see there in yellow that go up the rivers to the upside of this image here. The idea is to reduce the local flooding in this area by as much as 6 feet, which is pretty dramatic. And then since this project came to pass, there was a lot of discussion about those illegal crossings that Katie mentioned. And so they introduced a trail system, which also passes underneath the railroad tracks in a third box culvert section, and then meanders around and then crosses over the Allen Creek enclosure, shown in kind of a lighter blue there. And then a couple other items, the purple thin line near the bottom, there was a new storm sewer installed from Depot Street, which is just below this image here, to these hydraulic culverts, helping serve some of the local street drainage system, getting that water quicker to the Huron River and reducing the flooding. And then in another image, I'll talk a little bit about a disconnect of some Depot Street storm system to the Allen Creek enclosure itself as part of that as well. This is just kind of building on that overall plan view that we showed, and this is looking from the Huron River back at the project site. On the right, you can see that new pedestrian overpass over the Allen Creek outlet. Kind of in the middle, in the lower portion, you can see the twin boxes outletting. That's the new hydraulic culverts there. And then a little bit further up, kind of in the middle, is the pedestrian tunnel coming out of the underneath railroad tracks. And then this image rendering is from the other side of the tracks. On the right side, you can kind of see the pathway meandering down or heading down underneath the railroad tracks. And then to the left of that, you can see the weir structure where most of this flooding is being taken through the culvert pipes. So on the hydraulic modeling and analysis that was done to figure out the best solution and the sizing of the culverts and all those good things, HECRAS modeling was looked at initially. It was pretty limited. We have a 100-year peak flow here of about 2,400 CFS. The Allen Creek enclosure, as we mentioned, is much overpowered. That's only able to handle about 1,300 CFS. And so we ended up looking at using a swim model for this. We modeled the surface flow in 2D. We were able to take into account the impacts on the local connection system, and just gave us a better assessment of the design alternatives. And not sure if you guys will be able to see my mouse or not, but the Allen Creek enclosure basically kind of runs along the left side of the image you see here up towards the river and where it outlets. Along Depot Street here is the City Street sewer system, connects in many different drainage structures along here, and then that feeds over to the Allen Creek enclosure before continuing on to the river currently. This project, because that Allen Creek enclosure overflows so much, and when it does, it's extreme. The actual conditions would be you'd get backflow out of the Allen Creek coming up and popping lids off these catch basins along the street here, and just contributing more and more to the local flooding. So as part of this project, we did a disconnect of that local system into the Allen Creek outlet, and instead all of that system goes in that new 48-inch pipe that we mentioned earlier in purple there. Katie showed this image earlier, and just to kind of give an idea of what this project is doing and how it's changing the local flooding conditions. Again, here's the flooding that's occurring now at elevation around 780. You can see many of the properties that are within that reach there, including the railroad tracks themselves. As part of this project, that 100-year floodplain will be shrunk dramatically. The footprint of it is much, much smaller. And then this might be a little bit hard to see on your screens there, but that floodplain got smaller and took a lot of properties out of it. But in the top image, you can see here what it also did is it took the railroad tracks out of the floodplain, which that image is showing there. And in the lower image, pretty much all of the houses that are within this area, if they're still within the floodplain, that floodplain level is now in their basement and no longer on their first floor, which is, of course, a big deal with flood insurance and then, of course, damage to houses. So it's a very dramatic difference that the project is making. As we got into the design here, we're basically funneling water and people into one area. And the design of that weir was critical to ensuring this reduction in the flood area that we're looking at. And so that mix of pedestrians and potentially high flowing water at certain times presented a challenge, and the risks there we had to balance those. So we did incorporate some safety features around that weir. We're looking to put in some signage and some kind of thin profile fencing that's elevated a little bit above the weir to deter people from going in there during dry or wet times, but still allowing that flow to freely get through over the weir and through the culverts. And then you can see the tunnel for the pedestrians that goes through this wall that goes along here also acts a little bit as a flood wall. So when there's flooding going on and going through the hydraulic weir and into the tunnel, the idea is that this area in here will still be dry, cut off by the concrete walls there. Another challenge with pedestrians is the river it does fluctuate, the Huron River, as well as some groundwater getting to the river. And the railroad tracks that cross through this area are kind of a fixed object. So we were limited in how high we could have our pedestrian culvert enter underneath these tracks. And really by the bottom, we were limited by the Huron River and the groundwater levels, as we didn't want that pedestrian area to be wet. And so we were fortunate to have a USGS gauge station right near the Allen Creek outlet. So we had, in this image you see 5 years, but we now have about 7 or 8 years of data of water elevations in this area. And we went through and looked at how many days out of the year and how much time out of the year could this pedestrian portion of the culvert be inundated. And you can see here the dashed line was our original design that was bid and let. There was basically each year there would be a time where you would see some flooding. Very, very few times that it would be deeper than 6 inches, but at most it's about a foot. And during construction, it was nice because we worked with FEMA and some of the grant folks that contributed to this. And they agreed to raise that pedestrian invert 1 foot, which reduced our vertical clearance inside the pedestrian tunnel from 10 feet to 9 feet. And you can see the solid red line now is where our tunnel surface is, dramatically reducing the time of anticipated inundation periods. And then we installed a very cheap method of potentially being able to pump out some water if it does tend to pond in there a little bit. Or during maybe a cold spring where the river levels are a little bit higher and there's ice flows kind of jamming up the gravity flow system from the pedestrian tunnel. We installed a sump area at a low point in that pedestrian area, and that's kind of shown here with a star. The idea would be that they could drop a mobile pump inside that sump area, pump the water up to an installed catch basin that's in this area. That catch basin then gravity feeds to the river at a higher level. So if there is some local water just kind of accumulating in this tunnel and they need to pump it out for any reason, they would have that ability. And you can kind of see that same phenomenon here down in elevation view, where the Huron River levels are normally, the seasonal highs, and then the rough area here of where our pedestrian path is now today. So getting into the construction of this project a little bit and talking about some lessons learned, I'll go through some groundwater levels that we were aware of and tried to plan for, and a lesson learned there. And then the fiber optic cables that run along the railroad tracks, we had a good plan, a well thought out plan to work around those. The key here being that there was a very critical construction stage in this whole project where we were to build all these large culvert sections within basically a one-day outage, train outage, and that was going to be very challenging. So I'll talk about that a little bit. And then, of course, COVID came, which is probably a popular topic on a lot of projects being presented at this year's OTEC. So this first one is on the groundwater levels and dealing with groundwater during construction. We were aware of groundwaters were right around the area where we were setting our box culverts, and so that was going to need to be an issue. We initially set up the contract and the pay items that essentially shifted a lot of the risk for this groundwater onto the contractor. The groundwater itself was potentially contaminated, so it was going to have to be monitored and then treated before being outlet into a nearby sanitary system. And that fluctuating groundwater, of course, as things go with projects, it was up during the time that they were building this project. So it was probably at one of its higher levels that we had seen over the last 6 or 7 years, the river levels there. So the contractor, they did install wells to lower that system. They were pumping water out, treating it, sending it to this system, treatment system you see on the bottom image there. And they pumped and pumped and pumped and pumped. Well, because we got so much pushback during the original bid, the owner decided, hey, we don't want to push this too far into the contractor and have these bids be too high. We modified the contract language and the pay items to essentially shift the risk back onto the city. And at that time, of course, the contractor didn't care how much water they pumped. In fact, the more they pumped, the more they got paid. They were basically far, far, far over budget on this particular item for treating groundwater. And so that was a big lesson learned, that maybe we should have left that risk on the contractor. You know, if it would have went that way, who knows what the bids would have been. It's one of those difficult ones, but a big risk either way you go. Another one that I alluded to are fiber optic cables, which are popular along railroad tracks. These, in this case, there were 3 different lines or ducts that were running along the tracks, all on the same side of the railroad tracks. And we had went through and developed an elaborate scheme here to essentially build all of the new culvert system without train outages up to our temporary sheeting. You can kind of see how close the one fiber optic lines are to the sheeting. But our initial idea was to build these box culverts without the outage all the way up to this area and kind of hopscotch these and work around these fiber optics outside of a track outage period. The contractor, when they came on board, they had a different plan for doing this, and they thought it would be better. They convinced us that they could basically build or work around these fiber optics during the outage. It would be more efficient for them. We kind of deferred to them at the time, said yes, okay, and I kind of regretted it. Here's a few images from during construction. They did not break or hit any of the lines, which was amazing when you see these excavators working around the fiber optics. But what it did do is it dramatically slowed their progress. They had a lot of excavation to do here in the short window of track outage, and they were really hung up. The excavator on the left is not actually digging anything. It's just holding on to one of the fiber optics. The one on the right is actually doing some excavation there. So in hindsight, we should have told them, no, just stick with the original plan. I think the outage would have been much quicker in this case. And the last lesson learned here, during construction, we planned a lot for this being a very tight window. We were planning on around 22 hours of closure that we knew might get extended an hour or two based on the amount of work. We were also impacting and using the parking area of a private owner office building nearby. Had a lot of plans for off-site parking and all sorts of things, and coordination went on during design. And then COVID hit. So this outage was in May timeframe, right at the height of COVID. That private owner, they had nobody at work. So they had that parking lot all to themselves as long as they wanted it. Amtrak, that was another one. We were trying to maintain trains. There was 2 trains a day going through here. And that essentially dried up to almost nothing. So they were able to get an extended outage from Amtrak. I think we got to like 32 hours or something like that. The contractor, I think, got a little complacent and they couldn't even meet that. So we were originally at 22 hours. I think we ended up at around 36 hours of the track being out of time. So the funding on this project, just kind of run through here. The FEMA grant that Katie alluded to was the primary money source for the project. There was a couple of state grants, a TAP grant there, and MDNR, which tied in the pedestrian work. And then overall, the city kicked in about 1.4 million. Of that, about half of it was from their alternate transportation program. So with that, I have a quick video to share. We'll see how this goes, and then we'll be wrapped up. So this will be a time-lapse video of the that outage that occurred there. Right. Hopefully everyone can hear us there. That concludes our presentation here. I wanted to thank the City of Ann Arbor, MDOT, Bergmann led this project, and then we were supported with the hydraulics design by OHM advisors. And I probably should acknowledge that, yes, this was the City of Ann Arbor project that's being presented at OTEC. And I can say I hate U of M as much as everyone who's listening on the call here. So we're all in the same boat there. So thank you.
Great, thanks, Katie and Jeremy. A few questions came in, if you guys have a second. The first question is having to do with the floodplain elevation. was it able to be lowered even further than the, the top of the basement in those buildings, or what were the limiting factors as far as getting that floodplain down?
Yeah, so the question, as I understand it there, we had I think what you're saying is there's still a little bit of flooding that occurs during that 100-year event. Is that kind of the question there, Jonathan, do you think?
I believe the question is why did they stop at that point? What was that? Was there something magic about that point, or could it have even gone further had the project been changed?
Yeah, no, I think the flood relief design there was the capacity, I guess, of that weir system and the culverts to get the floodwaters out of there. It was optimized in a way to get as much of that flooding out of there as possible. But I think just the topography in the area, you're still gonna have there's a little bit of a bowl back there that's still gonna be in a flood system. So maybe the way to answer that is I don't know that we could have lowered those hydraulic culverts anymore to get kind of all of that area drained out because of the elevation of the Huron River. I don't know if that's the right answer to that question.
Okay, good. And then there was a question asking, as far as the groundwater, what was it contaminated with so close to those residential areas?
Yeah, that's a really good question. So on the north side of the railroad tracks, that DTE site that's being developed that Katie alluded to, that was actually all natural river area at one point. Back in the early 1900s, when that DTE is an energy company here, they built a power plant, and they basically just filled in and relocated the river over. Within that fill and over the years of a power plant being there, there's just been some nasty goodies in the soils in that area. And fortunately for our project, we were kind of outside the real hard limits of that. So I don't think there was a whole lot of bad contaminants in the area we were excavating and digging in, but it was very close to. And so I think the biggest thing was there was some actually naturally occurring also soils out here had some cyanide in the soils, but there were some other goodies from that power plant that were the major concern.
And then that treatment, so the treatment the contractor had to do, was that terribly involved, or did they just put it in frac tanks and get it to the sanitary system?
That's exactly what happened, and the contractor kind of took advantage of things because their fixed cost was set into a lump sum bid to set up those tanks, and then of course the discharge rate into the sanitary system is X cents per gallon. That was all fixed costs that we knew. But then they had this how much water are they treating item that per gallon was fine, but they just kept going and going and going and going. So those gallons just kept going up and up and up and up, which led to that big overage. And so it's a little bit of a dispute right now actively. I don't know exactly how much they'll come out on the positive side of that, but yeah, it was a fairly straightforward treatment.
Okay. Yeah, and I know we're at our time, but I'm going to try to get in two more questions real quick. First, the weir structure, did that get modeled in SWIM, or how did that work into that? How did you model that specifically?
Yep. Yeah, it did get modeled in there, and interestingly, if you look at our renderings, the weir originally had a different shape, a little more compact shape, but it had a little bit of a star, a little triangular wedge sticking out to get a little more weir length into a tighter area there. That triangle, however, went outside of the railroad property and onto the private owner's property. They were very they were against having any part of that weir on their property, so we did have to redesign that and have it more linear and just a little bit wider there. But yes, that was modeled, and part of the package that was submitted to FEMA and all of the oversight that they had on the project went through the ringer a couple of times with them.
Okay, and then when the new channel got put in, were there any negative ecological effects from the channelization of the water, or the change in flow regime? And I know this was a developed area that was being flooded, but was that considered being Ann Arbor and the effect on the ecology in the area?
Yep. Yeah, we did look at that, and fortunately for this area, there's not too much concern here. You know, the typical trees in the area, we have Indiana bat that we always have to worry about. So some of those were cleared. They just have to be done out of season. There were no mussels identified. It's kind of a turbulent area. It's down here at the base of the Argo Dam. It's downstream of the Argo Dam, which is right there. The Allen Creek enclosure itself pumps out a lot of water. So it's pretty turbulent in that area. Other than being in a floodplain, that was probably the biggest environmental, I wouldn't even call it a challenge. It was just making sure that we had the permitting there for this project.
Sure. Okay, well, we're 3 minutes over, so there's a few more questions, but Katie and Jeremy, I'll let you guys handle those offline afterwards. So let's go ahead and get into the next presentation. Jason Wise and Sean Milroy. Thank you, Katie and Jeremy.
Thank you. I'll turn this over to Jason.
We'll get this switched over real quick.
Yeah, doing that now.
While he's doing the switch, I'll start reading about Jason and Sean. Jason Wise is the design build project manager at E.L. Robinson Engineering in Cleveland. He received his BA and MS in civil engineering from OU. Jason has 16 years experience, including 10 years with ODOT and the past 6 years with E.L. Robinson, where he's managed a variety of projects, including he's currently serving as the utility and railroad coordinator for the Opportunity Corridor third phase project. Sean Milroy is the lead roadway engineer for the Opportunity Corridor Phase 3 project. He's project manager with Michael Baker International in Cleveland for 19 years. His 24 years experience include projects ranging from high-profile interstate and improvements to local road bridge projects. Sean is proud to be a U.S. Air Force veteran and ASHE Lake Erie section president. Jason and Sean's presentation is titled Replacing the Regulator. Turn it over to you guys.
Thanks, John. I presume you guys can hear me okay? Thumbs up?
Yes.
Yes? Okay, excellent. All right. I'd like to thank OTEC and John for the introductions, for letting us do this presentation today. So I'm going to drive and I'll take the first part, followed by Jason, and I'll wrap it up. So we're replacing the regulator. And go. All right. So a little background on this project in its entirety is the Opportunity Corridor is on the southeast corner of Cleveland. 490 currently dead ends at East 55th, and the impetus behind the project was to bring economic development as well as allow people on the west side an easy access to University Circle up here. University Circle holds the VA Hospital, Cleveland Clinic, University Hospital, the Natural History Museum of Arts, the orchestra. So we wanted to get folks from the west side to here. Part one of the Opportunity Corridor was the design bid build, and it was the rehabilitation of East 105th Street here. Part two of the Opportunity Corridor was a design build project, starting at this limit of part one, installing a new RTA, the local transit authority station, and bringing the work to East 93rd here. Our project, the one Jason and I have been working on for 2 years now, right, is Opportunity Corridor Part 3, which is starting here on the west side from 490, bringing a corridor boulevard style through the existing neighborhoods, tying in at several at great intersections. And we are wrapping up the design at this point. A little blow up for the entire section 3. Currently 490 comes into East 55th and dead ends. We're bringing the Opportunity Corridor underneath East 55th, and that's the impetus and the big part of our project today. Access to 55th is using the Quadrant Road here. Access in the neighborhood to get to an RTA station located right here in the northeast corner is over a pedestrian bridge we're installing. As we head to the east, we go over RTA's test tracks where they test out new and updated equipment, repaired equipment. Kinsman is one of the at-grade intersections, so we can maintain access to the existing neighborhood. We go over a pair of split bridges over RTA's blue-green line, the passenger lines. East 75th Street is another local tie-in, and the new police station for City of Cleveland is going to be located in this area. East 79th Street, Orlando Baking, an institute of Cleveland, has been around a long time, is here, and they're excited to get access to the interstate. As we continue, we go underneath Norfolk Southern lines here. And then as we wrap up the finish line, we come at grade with Buckeye and at grade at Woodland. This particular intersection requires switching this East 89th Street bridge to a PED bridge only, and then we tie into Opportunity Corridor Part 2 here. It's 6 signalized at grade intersections. There were 2 BMPs for this particular project. We installed new sanitary and new combined sewers for the economic development along the corridor. Part of the project is giving a bunch of the right-of-way back to the city of Cleveland for future development. The regulator is what we're going to talk about today. 7 bridges. One was the railroad bridge I talked about, and the 2 PED bridges. And there were 4 sets of retaining walls on this project as we either jumped over or ducked under various parts of the project. For those of you not familiar with design build, this project was broken into 29 buildable units. A buildable unit is a standalone set of plans that the contractor can get going on. Currently, we're 35 buildable units. It was a team effort without any doubt. 20 of the buildable units were Michael Baker's responsibility and 15 were subs, but there was sub involvement in all of them, and Michael Baker had oversight of all of it. It was a team effort here. And as of today, 34 of the 35 buildable units have been released for construction, which means the contractor can get going on those. This is you, Jason.
Okay, morning. So I'm going to talk about utility coordination, which will kind of set the stage for why we're moving this regulator, and some of the hurdles we went through. Somehow I was dubbed the utility third party and railroad coordinator for the project, which has been a challenge for the past 2-3 years, but we've overcome most of it at this point. Coordination, of course, with ODOT, which is the owner, City of Cleveland, different entities within the City of Cleveland, Northeast Ohio Regional Sewer District, which is the maintaining agency for the regulator, Norfolk Southern Railroad, which we go under with the boulevard, as well as an outfall sewer will be tunneling underneath another one of their lines. RTA, commuter rail, we cross over them 3 times, and we also reconstruct their parking lot at their station on East 55th Street, which is part of this presentation as well. Every private utility known to man and woman in Northeast Ohio, except for steam. It's the only one we didn't find. And of course, community action groups and any of the local businesses, such as Orlando Baking. So East 55th Street runs north-south at the major north-south route in the east side of Cleveland. And as part of this construction, we are building a new bridge to pass 490, which turns into the boulevard right underneath East 55th. We need to build a new bridge at that location, which impacts the existing regulator. So that's the impetus for relocating the regulator south of the existing bridge. As I said, every utility comes through this area. So somehow we need to maintain those utilities throughout construction, also maintain access to the RTA parking lot for passenger trains, parking, bus pickup, etc., as well as maintaining flows to the existing regulator. So how we accomplished this was, Sean, if you go to the next slide. Here's a list of the existing utilities. We had 2 different power companies, CEI or First Energy. They had 4 overhead lines, 2 11 kV and 2 5 kV circuits that feed the RTA, both their rail and their maintenance facility. AT&T had fiber and copper lines. Dominion had 2 gas lines. We had a 16-inch sanitary forced main, 2 water mains, a 12 and a 30-inch water main, which we needed to maintain the 30 during construction. And then Cleveland Public Power had facilities through the area as well. This capture, this is East 55th running south and north as you head right on the page. I'm not going to go over everything in detail, because that's not what we're here to talk about, but in the center of the screen is the regulator and its various feeds and outlets. But this kind of just shows all the spaghetti mess that we had on East 55th Street. And then to the right, you can see the new bridge, which will carry East 55th over the Opportunity Corridor passing underneath. The best way to see these existing utilities, of course, is in a cross section. So here's actually a transverse section of the final configuration of the East 55th Street Bridge. Working left to right, we had 7 days on the bridge. The scope prohibited us from putting any utilities on the outside bays of the bridge. So in bay 2, that's the 16-inch force main. Then we go to bay 3, which has both CPP duct and AT&T duct in the same bay. The next bay houses a 12-inch water main, followed by 2 gas mains, and then finally the 30-inch water main, which required a special cross-ring configuration. And then we actually put CEI, or First Energy, up in the sidewalk, and 8 different conduits there, since the sidewalk was so thick. So that kind of gives you an idea of what we had to cut across to get this regulator in place. So in order to maintain these facilities, it just so happened that maintaining vehicular traffic, we had to construct a temporary runaround road around this intersection of 490 and 55th. So ODOT allowed us to shut down 490 for 2 years and detour that traffic elsewhere, maintaining one-lane construction on East 55th with this runaround, which is in gray, and Sean's following with this highlighter. So this provided a path for utilities to follow. So we created a trench, Sean, if you go to the next slide, that they could share as a common facility. So a temporary water main, temporary AT&T, temporary electric, and temporary gas main, all within this utility trench that follows our temporary road. Not all of them elected in the final configuration to use this, but it was provided, and that definitely facilitated faster construction. So again, going back to this temporary configuration, you had most of the utilities running underneath the temporary road, and then we also had the temporary 16-inch sanitary force main, which we had to maintain while the regulator and the bridge are being constructed. So we followed a path along the west side of the alignment of 55th, and that allowed, once all this was complete, that allowed the regulator to be constructed, which is basically a 2-story house. It's underground in the green box, as well as the bridge construction on 55th, which was constructed at grade during this period. And then this is just showing the final configuration with all the bold utilities running through after the regulator is completed. This is currently where everything has been constructed, and everything's live. All the utilities are live. The bridge is complete, and we are running 2 lanes of traffic on the west half of the bridge at this time. So I think that pretty much summarizes, Sean, what we've had out there for the past 2 years, utility-wise.
And the best part is that was just to get to the regulator and start the new regulator. So this is, pictures 1,000 words. This is for I-490 when it was open, and this is when we were, building the runaround, and this is where the temporary utilities are going to go, such that we could get in here to do this particular bit of work. This is it in its final condition. This is when 490 closed for the 2 years Jason talked about, the temporary runaround, and you can see in this little blob here, this is where they're starting to dig, as Jason alluded to, the house. It's impressive. This is a slightly different picture. So now we're looking to the south. This is the RTA station where this is the station we're maintaining with buses and pickups. Here's the runaround. And what you're looking at here is the relocated regulator and where the bridge is going to go and the existing regulator. This pit here is going to be the tie-in to not only the stormwater we're proposing, but the existing regulator system kind of out of the way of not only the opportunity corridor running here off the screen, but the new bridge itself. So why are we replacing it? Well, great question. This is where the new bridge is. So this is a profile view of the East 55th Street Bridge. And this pink outline is the existing 96-inch brick sewer. You can see here, this is opportunity corridor westbound coming out, and the eastbound heading underneath it. And well, nobody wants to drive through a brick sewer, so that was what we ended up doing is bulkheading the 96-inch brick on either side and then filling it in for the installation of the bridge here. What you see down here is an existing 78-inch storm sewer that runs to the Cuyahoga River here in Cleveland. Construction photos again. This is looking to the north. This is the west side of the project, if you will. What we did is we did top-down shoring for the regulator. So as they continue to dig the earth out to get down to where we needed to be to get to the 96 and the 78-inch storm, they can continue to install the different lagging as they got deeper and deeper. This is again looking to the north. You can see the whaling system starting to appear as we get deeper into the existing ground. This is the existing 96 this fellow here is standing on. This picture flips the view. You're now looking south. Here's the 96-inch that we were looking at a minute ago, and this is the combined sewer. This is the 7 to 8-inch overflow that is storm only. This is, I'll give you actual dimensions, but the top of this is about 45 feet deep. This picture tells it all. This garage / house Jason was talking about is 24 feet by 36 feet. And to get to the bottom underneath the 7 to 8-inch storm, we went 50 feet underground. For those of you that don't know quite what a regulator does, is the existing 96 sewer brings in combined sewers. Combined sewers is the sanitary and storm back in the old times when the solution to pollution was dilution. They just mixed it all together. Currently, NEORSD is trying to pull all of those apart. And that's one of the items we did for this particular project, was to help them in their long-term plans. So the existing 96 comes in here from the south. Our proposed combined sewer comes in here from the southeast. And what it does is it leaves this proposed 48-inch that goes to the storm sewer plant heading out this way. During a rain event that exceeds the capacity of the plants, because we don't want to flood the plants out, we put a restrictor plate here on the outlet for this 48-inch. When the water levels get too high, they jump this adjustable weir we installed. The water jumps the weir, goes down to the lower chamber, enters the channel, and heads out to the river. Not ideal situations, but currently NEORSD is improving their systems, and that's why this plate is adjustable, as well as the orifice plate. So as further systems come on down line, this orifice plate will get either raised and or removed, and this weir plate will get raised, continuing more of the storm sewer, combined sewer going to the treatment plant, not jumping the weir and heading out to the river. The part of the exciting parts of this particular installation was, you saw the outline of the box here, this outlet pipe to the storm sewer plant and this inlet pipe for the proposed stormwater we're doing had to be jack and board. It wasn't a straight shot. We weren't going to open up and open cut 50 feet underground. So what you're looking at here, oops, did I go one too many? I did not. So what you're looking at here is that the regulator's online today, and as Jason said, the bridge is actually open. This is an older picture, but this was the runaround. This was the contractor filling in the regulator. We were able to do everything offline, allowing the regulator to keep going, hence those previous pictures where the pipes were still encased, until we got the connections over here set up correctly. Now that those connections are operating, they filled in the regulator here, and this is the beginning of the excavation that will take 490 underneath the proposed bridge and continue it to the east. That is about all I have. And Jason, anything else you want to add before we open up the questions?
No, I think that's it.
All right.
Well, great presentation, Jason and Sean. I know I had a question. We don't have too many questions come in yet, but I had a question. For that regulator, do you know about how often the combined sewer overflows as it is into the storm?
I believe it was on the order of 6 to 8 a year. And I think as the improvements come on, they're trying to get that down to 4 or 5 times a year. It happens more than anybody likes, and they're currently working to improve that. I know we had several iterations with the sewer district to come up with what their best estimate was based on all their modeling for the entire system and what we could get away with. Hence those two fluctuating, not only the weir plate, but the orifice plate, because they're hoping to have some new systems online as well as improvements at the plant for storage at the plant. But I believe it was a couple times a year.
So the idea is you take off that weir plate to the 48-inch and have it go stored at the plant somewhere eventually, and then that gets treated as opposed to sent to the stream.
Correct, yes.
Gotcha. Okay, well, I don't think we have any other questions come in yet, unless I'm missing something, Paula, but I think we're good there. So if there's no other questions, we'll get on to the next one. So Jason and Sean, thank you very much for your presentation.
Thank you.
I think you can go, I'm actually presenting this next one, so you can go ahead and transfer over to me.
All right.
So Justin and I. So while that's transferring, I'll go through just my intros. So I'm John Prier. I'm the environmental hydraulic engineer in central office. I do post-construction BMPs. I've been in Columbus as an engineer for 14 years, at ODOT for about 7 years. So I work with post-construction BMPs here at the state. And Justin's a project manager for MS Consultants in Pittsburgh, specializing in hydraulic analyses, green infrastructure design, and erosion sediment prevention. He's a licensed PE for Ohio and Pennsylvania, and a certified professional in erosion sediment control. And Justin and I are going to be talking about this research project that ODOT has been working on for a while and will continue to work on. We'll get into this in just a second as I'm attempting to show my screen. Let me make sure I'm showing the right one. All right, Justin, are you seeing the right one, or am I looking at the wrong one?
Nope, that looks good to me.
All right, so let's get into it. This is the ODOT research project for soil amendment for stormwater volume reduction. And we'll get into what that means. That's kind of a wordy title, but we'll get into it. So this is done under ODOT's stormwater program, stormwater research project, and there's a lot of ODOT stormwater research. Hydraulics has been heavily involved in research here in central office. So this is one of our exciting new ones. So the first thing I'll get into is what are we dealing with here? What's the problem? So ODOT has a lot of roads that look like this, right? A lot of pavement, a curved road. The edge of right-of-way is relatively close. There's a curb. So most of the water that goes onto the site goes down underground and is basically very difficult to treat with anything except a manufactured system. So you can see the manufactured system on the right, an underground vault, swirly device, whatever. So we put these in from time to time for post-construction BMPs. So when we do construction, Ohio EPA construction general permit requirements require us to put in a post-construction BMP. And this situation happens kind of a lot. So and there's nothing wrong with these manufactured systems, but they don't work in every situation. ODOT also has a lot of roads like this, where there's no curb and there's a median infield or a median area where water sheet flows off the road into the ground. So our thought is, can we take better use of the research project came about because we'd like to do less expensive underground vaults if we can, and more taking advantage of the relatively unusable space right next to the roadway where we have this area that sheet flows off into the grass. Now we already do this in some regards, but we wanted to enhance our ability to treat this area. That's where we really got into the thought of, what would it look like if we amended these filter strips, these grass areas where water sheet flows off the roadway, amended it with some soil amendment, some sandy or some type of soil. What can we get as far as a level of treatment standpoint to help ODOT find a cheaper, easier way of meeting our post-construction BMP requirements, less requirements to buy up right of way, less easier to maintain, cheaper to build, and taking advantage of the space we already have that isn't otherwise being used. So, our thought is that this could even be done in situations where you might have difficulty. So this is a interstate down in Cincinnati, ODOT, that's I-75. So there's areas there that are difficult to treat. I know it's a little fuzzy there, but if I zoom in on that area, pretty much curb to curb pavement. But if I look just north of there, there's a big median area in the middle with lots of grass. So the idea is, can we over-treat in one area, or can we provide treatment in one area and not provide in the other area? So, and I want to bring a distinction here that a lot of people don't realize. ODOT has two different tiers of post-construction BMPs. One that we call quality only, which helps get out all the pollution, or the basically total suspended solids, and one that we call quality and quantity, which helps reduce the runoff. So those are our second tier BMPs that we have to do on some of our bigger or more complicated projects. So those projects, those types of BMPs that we get extra credit for or are required on some of our larger projects are things where you'll see detention basins, bioretention cells, or infiltration trenches. We almost never see infiltration trenches because almost all the soil in Ohio is hydrologic soil group C or D, which is not great for quick infiltration for a post-construction BMP. We have very little A and B soils. So we almost never use infiltration. And we do have some detention basins and bioretention cells, but some detention basins sometimes require extra right-of-way or extra safety requirements to keep the traveling public out of them. And bioretention cells are great, but they can be more expensive in some situations. So we wanted to say, is there something we can do? Is there credit we can get for really knocking down the runoff in these soil amended vegetated filter strips and land that ODOT already owns and is not using and doesn't have a way of using because it's within the clear zone? So is there some way we can get credit for that and really save a lot of money and develop a new post-construction BMP for Ohio and maybe for other states, because this research is very applicable. And really that's a really big deal for ODOT because we don't have a lot of new post-construction BMPs. There've been about the same 7 or 8 for the past 20 years. So this could be a really big jump for post-construction BMP treatment for roadway projects in Ohio, and then also facilitating it across the nation. And I want to bring up off-site mitigation. So, because it ties into the same question. This soil amended filter strip is not just beneficial in sites where you have a construction project going on, but if you have a construction project going on nearby and you have a site that's not applicable for soil amendments, the idea is that you might be able to mitigate. So Ohio EPA in general, ODOT works well with Ohio EPA. For their construction general permit, they allow underground systems, but they don't like them. They prefer these more green infrastructure type systems, volume reduction type systems. ODOT doesn't like buying up right away for detention basins or for any of our post-construction BMPs. Ohio EPA allows this off-site mitigation where you can see the two areas. There might be a project to the south that doesn't, or a project to the north that has trouble treating, and a project to the south that has an easier time treating, and we can provide extra treatment at the southern one to make up for the treatment requirements of the north one. So both ODOT and Ohio EPA would rather put BMPs in these open grassy areas where we can see them and maintain them and keep an eye on them, as opposed to big vaults or manholes under interstates. So it's really, if it works, it could really be win-win on whatever kind of bottom line you want to call it. So the questions we have are, how much, the research questions that develop this whole thing are, how much credit can ODOT get for these amended filter strips? We know that they're not going to treat 90% of the average annual runoff. We don't think they will, because that would be a very sandy soil. So we think we're gonna need to have some treatment ratio. And what do those amended filter strips look like? What kind of soil are we gonna use? What kind of amendments? How deep? How big? But our general idea is in these instances, instead of building expensive underground vaults or buying up right of way for detention basins, or even putting in detention basins where it's less safe, instead of doing that, how many acres of this nearby interstate, which we have almost unlimited amounts, and even local transportation agencies have a decent amount of area that sheet flows off a roadway into a grassy area. How many acres can we treat? If we had to treat 5 acres at this site that we're gonna go to an underground vault, can we treat 5 acres, 7.5 acres, 10 acres of amended soil and get the same apples to apples treatment? So that's what we're looking at here. And that's really what set off this research project. To develop this brand new post-construction BMP. And it's nothing fancy, it's just a amended soil, but it's really used in a way that we're trying to make it safe next to the traveling public and cheap for ODOT and basically meet everyone's needs. So it's really making use of this large amount of space that ODOT has for both retrofits of existing projects or for offsite mitigation and for new construction projects. So our research team is MS Consultants, USGS, and Stone Engineering. It started back in May 2017, and it's going to all go through all the way through December 2021. So it's a very big, one of our biggest, probably hydraulics, about largest research project to date, and it's getting going. So that's all the fun stuff. That's all the idea stuff that we came up with. I'm going to turn it over to Justin for the nitty-gritty of the details. Let me turn it over to Justin here. Give me 1 second. All right, get it up to Justin. And Justin will pick it up from here and talk about the whole setup of the research.
All right. Thank you, John. Let's see. Let me know when you can see my screen. Let's see here. All right. Can you all see that? John, is that showing up okay? Okay, yeah, so as John said, I'm Justin Kerns with MS Consultants, and give you some of the more details about the research project we've been working on with ODOT since 2017. The first step in the research project was to figure out where our monitoring sites are going to be located. So you can see here, here we go. So we're looking at monitoring sites that are along ODOT right-of-ways, ODOT roadways, and we're primarily looking for large, wide medians as well as side slopes off the roadway on non-covered roadways where we could study the feet flow and the impacts of soil amendments. We want to make this soil amendment BMP applicable to any site in the state of Ohio. So one of the key aspects we looked into was distributing our sites along the 3 different rainfall zones, based on the ODOT LND Volume 2. These are 3 different rainfall zones, and so they're going to have a little bit different characteristics in terms of how much rainfall and what intensities they receive throughout the year. So just to kind of cover our bases, we scattered our sites, across the state between kind of Columbus and Akron. We're going to be in all 3 zones, but still keep them close enough so that our maintenance crews could go down and inspect the sites without having to make it a multi-day trip to cover the whole state. This began with a desktop exercise where we used videos and aerial imagery to identify some key spots that looked promising, where we thought we had enough right-of-way and enough space to work. And what we found out was upon going out and field verifying some of these sites that we identified from the desktop exercise, was that the center medians of the roadway turned out to be best for our monitoring locations. ODOT has a lot of these, 2-lane kind of divided highways with a big, wide, grassy median, and they kind of met all of our criteria. They are totally within the ODOT right-of-way, which made construction an ease. We didn't have to worry about property lines and accessing sites, going through private property or anything. So with that, pretty consistent lengths and slopes and widths is what we're looking for. We're trying to control as many of the variables as we can and isolate the ones that we want to look at, obviously. So a nice consistency of the medians is a good thing. They offer good protection, and what I mean by that is that.
Yes, sorry, real quick. Your volume's coming in a little fuzzy. Is there any way you have a different microphone situation?
Let's see. Unfortunately, I don't know what I can do about that. I can try to speak up a little bit if that helps, but.
Sorry to interrupt. I know I hate doing that.
No, I appreciate you letting me know. Let's see. Let me try this. I don't know. I wish there was something more I could do. I can
Justin?
call in from my phone audio if that would help.
Yes, Justin, call in from the audio. Go ahead and click in the audio section and then click phone call, and it'll give you the instructions to call in.
So bear with us for just a moment. Believe me, it's worth the wait. There's lots of good stuff to come here about ODOT's research projects.
And maybe, Jonathan, we can ask the question that came in.
Sure, let me look and see the question. The question is, do you think that let me open this up all the way. Do you think that a bed of gap graded number 1 to 2 limestone aggregate is more effective in providing water quality when compared to water quality basins or grass strips? So basically asking about putting in some big rock, number 1 and 2 are big rock, are more effective. So yes, we looked actually, and Justin's going to get a little bit into the soil amendments here. We looked at the potential for larger aggregates. There's a lot of issues with that. The one is just that we wanted, part of the goal of this, and Justin will talk about this, was to keep things as cheap and implementable as possible. As soon as you start putting engineered media underground, which I would consider, excavating and putting rocks, whether or not you bury them under some kind of sand or not, more of an engineered media, it gets a little more expensive quickly, especially when we're doing large areas. So we really wanted some kind of sand or material that we could compost in quickly. So we did consider rock, but the costs got us pretty much out of there. We wanted to stay relatively shallow and without large costs. So Justin, are you back on with the volume?
I am, yes. Is that any better?
That's much better. Thank you for switching over.
Sorry. No, absolutely. Thank you for letting me know.
We'll let you go now.
Okay, yeah, no problem. Yeah, so it said good protection, I think, is where I left off. And what we mean by that is that we're installing this monitoring equipment. It's going to be an obstruction. So we want to put it in an area that's protected from any kind of vehicular traffic. We don't want a car going off the road and hitting the equipment or one of our maintenance workers during maintenance or installation. So we found that when we were looking at monitoring locations, especially near bridge overpasses or bridge abutments, they had good sections of guardrail where we could install this equipment and keep it protected, both the equipment and the personnel from traffic. It also has a high percentage of roadway sheet flow. Again, for the most part, these roadways are center crowned, so you're getting at least one lane of traffic draining in each direction towards the center median. And this is helpful because, while we're looking at the stormwater runoff reduction, we wanted a high percentage of flow to come from the roadway as opposed to off-site drainage area. Any off-site flow that wasn't going to flow over our amendment was just going to be more noise and more data that we're going to have to, account for in the results. So by keeping a high percentage of the flow we really want to treat, we're just going to make the data analysis a little easier. These medians have catch basins that ended up being pretty ideal for installing our monitoring equipment, which I'll show you some pictures later on. Our flumes and equipment could just bolt right down to the precast concrete catch basins. So based on all these factors, we ended up choosing 10 sites to be amended, as well as 2 control sites. They were going to remain in the existing condition in both pre and post, just to give a control from one year to another. That was to account for, if one year was particularly dry versus another year being extra wet, any kind of factors in the weather patterns that we could identify is what we want to keep those control sites in there for, just to give us a benchmark. So we ended up choosing these 10 amended sites. And again, you can kind of see here, we dispersed them across the different rainfall zones. And we looked at just really balancing factors like percentage of contributing right-of-way drainage area, side slopes, cross slopes, length, all those factors. We want to kind of be able to cover enough parameters to identify what factors impact the runoff percentage the most, but at the same time, be able to isolate the factors that were in our control, such as the amendments, to see how beneficial they were. Here's a picture here of one of our sites on 161, just outside of New Albany, fully installed during our existing conditions and monitoring. I'm going to break down some of these components a little more, but if you're driving down the road and you see something that looks like this, that that's our equipment. There we go. This picture here shows some of the more detailed information about the equipment that we're using. And I won't go to great lengths to explain all these things, but some of the key components were solar panel. This was used to power all of our monitoring equipment. And then a battery that the solar panel charged so that it could keep running 24/7, day or night, whether there was sunshine or not. There was a wireless modem. This used cellular data to transmit the data in real time to the USGS website, so we could constantly be receiving and monitoring the flow data minute by minute as we received it. The bubbler, in conjunction with the stilling well, is what we use to gauge the stage or the water depth within the flume. And what that does is there's a connection pipe between the flume and the stilling well. So the water elevations in those two pieces are exactly the same. And the bubbler is the tube that blows air bubbles into the stilling well. And depending on how high the water is in the flume, it requires more pressure to blow the bubbles. And so that's how it determines the height of the water in the flume, which I thought was kind of interesting. We also installed a camera so that we could remotely monitor these sites, again, through the USGS website. And this was useful, one, to kind of verify data, make sure everything was working correctly, as well as if we noticed any debris or trash, anything in the flume that may affect our results, we'd be able to see it visually and know that we need to send a maintenance crew out to address that. So the camera was a useful piece. And then obviously the rain gauge, another important aspect. In addition to measuring the flow running through the flume and in our site, we also measured the total rainfall falling there. Two valuable pieces of information. Here's another picture, again, showing the solar panel and a little better view of that camera. The flumes are just, it's an H flume. And then we also installed these wing walls, kind of, this is actually an improvement we made after everything was installed. And that's just to capture as much flow within the channel as we can and sort of mitigate any flow that would try to bypass our flume. We want to really capture all the water that's sheet flowing off this roadway. And so the wing walls help, capture that water, not let it bypass our monitor. Here's a picture here of the flumes in action. This would have been in 2018 after they were installed. And you can see they record quite a bit of runoff. And the camera, again, this is from our camera mounted on the monitoring equipment. So it was good to see them working. And you can kind of see that stilling well here, how that water surface elevation is equal to the water surface elevation in the flume. And that hose there is from the bubbler. And this pipe is laid, horizontally, to connect the two. Giving us pretty good, very accurate results. The next slide here, this is the gauge data from the USGS website. This is all publicly available information. I'm sure if anyone would like to request it, we could get you the link so you can go on the site and look at it for yourself. But it records the flow, the stage height in the flume, 24/7, minute by minute. And you can also see the rain gauge information to see how much rain were received at each site as well. And again, yeah, all available 24/7. This next slide here, this is a quick snapshot of one of our BMPs, or excuse me, one of our sites. This is again existing conditions prior to any amendment being installed. But it just shows that based on some partial data, this graph shows the amount of rainfall that was received and the corresponding runoff generated from the site. And from that, we were able to interpolate a best fit line to equate the amount of rainfall and how much runoff that's going to generate. So the idea through the soil amendments is that we want to reduce the volume of runoff that occurs during these rainfall events. So we want to see this line flattening out in the post-amendment monitoring, where the same amount of rainfall will result in less runoff. All right, this next slide here, again, just a brief snapshot of all the different sites, all 10 sites plus the 2 controls. And you can see the drainage areas, the longitudinal slopes, how much rainfall was actually received at each site. So quite a difference from these sites were on 161, and then this site was further north. So in this year, 2018, pretty decent disparity between rainfall received. This is the volume of rain, essentially, that fell on our site, just the depth times the drainage area. And then this is how much runoff was generated or measured by the flume at that site. So from that, we're able to calculate essentially the percent runoff, the percent of the total volume of rain that fell on our drainage area that actually was turned into runoff and measured by our site. And again, I'll point out just, it's interesting to note the disparities and the wide variability in the percent runoff from site to site. And this can be explained through wide variety of reasons, everything from antecedent conditions. Did these rains occur back to back when the soil was totally saturated and there was less room for infiltration? There's intensities, durations of storms. All these factors will play into what percentage of rain actually turns into runoff at these sites. Next slide. So after we monitor the existing conditions for the first year, we establish the baseline, kind of see how these sites are performing currently. And I guess I'll just note that some of those sites are only generating 25, 40% runoff in the existing conditions. So it makes you wonder, I guess, how much runoff is actually occurring currently. So it's just something interesting to look at. But we then turned our attention to developing the actual amended soils. We looked at a wide variety of materials. You can see in the list here: compost, sand, gravel, some different materials like biochar, crumb, rubber, expanded shale, gypsum. And we wanted to look at things, as John was saying earlier, cost effectiveness was very important. We also want these materials to be readily available in Ohio. We want contractors to be able to order these materials so they can actually install these amendments easily, and that will also relate to cost effectiveness if it's readily available. The key performance benefits we're looking for are to improve infiltration, improve exfiltration, and evapotranspiration, pretty much anything that will reduce the volume of runoff. We also want to make this a resilient and hardy BMP. We don't want high maintenance or anything special. The idea, I think, is to amend this soil where no one really even knows it's there. It just works kind of in the background. It does without any, maintenance. So we want good soil stability, resist erosion, and then we also want to be able to grow grass on this easily. So improves vegetation growth as well. So we analyzed all the number of different amendment materials and ended up choosing 3. We have the compost, sand, and expanded shale. These are the 3 materials that we felt gave us all of the performance benefits that we wanted, but were also cost effective and available in Ohio. So the amendment design is going to be comprised of these materials in different combinations. We have compost and sand as one mix, and compost and expanded shale is another mix. And then we also wanted to test varying depths to see if amending the soil deeper provides better performance, and if that additional depth is worth the additional cost potentially. So ended up with 4 different mix designs of the 2 materials at 2 depths. And we wanted to keep, again, to kind of keep as many variables consistent as we could, we kept the percentage of each material consistent throughout the design. So we could really see head to head which materials performed best, and then if the cost effectiveness of each material, which one's going to be the most cost effective and give us our results. Okay, so then next we went to the construction portion. And the construction was done in these kind of major steps would be ripping the soil. That just loosens everything up, makes the work a little easier going forward. We excavated by essentially just scraping off the top 2 or 4 inches, depending on the depth of the installation. We then added the amendments, the compost, the sand, or the compost and the expanded shale. And then rototilled all that together so that it's all one homogeneous, mix. It's an amended soil, so we're mixing it in with the existing soil, as opposed to laying just a new layer of soil on top of the existing. We really want to mix it in there and amend it. We then did some compaction. This is primarily from a safety perspective. We want to keep the medians, especially since they're so close to the actual driving lane, relatively firm. We don't want a car that may accidentally leave the roadway to, their tire sinks in and cause a rollover hazard, or if an emergency vehicle needs to cross through a median, we want it to be stable enough that you can actually drive on it without posing too much of a safety risk. And these are maintained by ODOT mowing crews, so they have to hold up to that same, load as, a tractor and a mower that any other median would. So they're compacted. We then topped it with a compost blanket just to help promote the vegetation growth and the seed added on top of that, and then an erosion control mat temporarily, while the vegetation took hold. And we found that we were able to retrofit about between half an acre and 1 acre site in about a day or two. So here's some pictures I'll go through and just show the process. Here's the ripping of the soil and then the excavation of the top layers. You'll notice that we kept the bottom of the median untouched. And the idea behind this was this BMP is targeted towards sheet flow. And so we left the bottom untouched because we don't really we wanted to eliminate the impacts that the channelized flow may have. So the only opportunity really this BMP has to infiltrate is going to be during sheet flow on the side slopes. Once it reaches the actual channel bottom, it's traditional untouched soil. So this was also used to maybe analyze if we're going to install this amendment on the outer sides of the roadway where the flow may run out of the ODOT right-of-way. There may not be a channel there to modify. So we really wanted to isolate the performance of this soil amendment on the side slope itself and its impacts on sheet flow only. Next, we added the sand and compost. This is just added as a mixed, layer on top of everything. And then we brought in the rototiller next to mix it all together. So it's one amended soil layer, and then the compactor came through. We compacted it to satisfaction. Next, you can see here they're spraying the compost blanket down. Again, this was a layer just to help with the seeding, so we get the vegetation to pop up as quickly as possible. We didn't want to wait a whole season for the vegetation to reestablish. We wanted to jump right into post-amendment monitoring, so this helped just speed that up. And that compost blanket was installed to prevent any erosion while the vegetation was establishing. Here's a completed site right after installation. This would have been in mid-April 2019. And you can see the flume, the equipment, all that remained the same. And you can see our 2 amended side slopes. Then this next picture was taken in May of 2019, just a month after installation. And you can see the vegetation starting to bounce back. And then the next picture I'll show you is in June of 2019. So another month after that, 2 months after installation. Vegetation is pretty well established at this point and came back looking good, pretty dense vegetation. Here's some other little quick preliminary data that shows, just kind of based on the initial data, some preliminary pre and post monitoring results. As you can see, this is at 1 BMP, but we're showing a pretty good trend that's showing us that the amendments are reducing the volume. This is the percent of volume runoff. And pretty much every month of this year, and then the total cumulative runoff volume has been lower in the post-amendment monitoring than the existing conditions. So we're showing some positive signs that this is having an impact. Our next steps are going to continue post-monitoring until the end of this year. And then once all the post-amendment data is collected, we're going to start reviewing and analyzing the results. And again, there's a lot of factors that we're going to be weeding out and deciphering. So the analysis portion is going to be very fun, figure out what the real true impacts of these amendments have been and what the cost benefit is going to be. We then are going to coordinate with regulators, Ohio EPA, to work on, getting this as an approved post-construction stormwater volume BMP. And then, of course, we'll make our recommendations to ODOT. We're going to recommend the most appropriate design, materials, depth, construction sequencing, We're going to produce standard drawings and specifications for the amendment, and then see what ratio of amended soil is needed to treat it, what percentage of impervious area that they have out there. So very, very exciting stuff to come as we start digging into these results and coming to a final conclusion on the effectiveness of soil amendment for volume reduction.
Great, thanks, Justin. So I'm going to jump
John,
right into
anything else to add?
We have a few questions in about 2 minutes to get to them, so I'm going to get right into them. So did we consider pollinator habitat as natural filtration? We didn't look at plants. Since these are right next to the road, this area where we have to keep good line of sight. So we really concentrated more on the soil, and we're planning on just regular ODOT grass. We have a permeability goal to achieve. We didn't. We wanted to get as much as we could while still running a smooth drum roller over it once, so we felt safe about a car not catching if it got there. So basically, we didn't have a specific permeability goal. It's not like an infiltration trench where we got to get a specific, at least 0.5 inches per hour. We weren't expecting that. So we're just kind of seeing what we're getting. The next question is the monitoring station only active during the monitoring time or during dry weather periods or wet periods? We left the monitoring station active all the time. We have a lot of pictures of nothing happening, so that's fine. Someone asked about getting the data. We will have the data at the end of the project. We won't release the specific empirical data in the middle. Like Justin said, we've collected almost all the pre-existing and almost all the post conditions. Things will be monitoring for about another month, and then we're going to crunch through them. So we really have to do our negotiations with Ohio EPA before we make all that public, but it will be there eventually. So talk to me in a year. Did we do grain size analysis for the media? We didn't, but we used ODOT fine aggregate sands, so that has a specific grain size that it meets, and we used the expanded shale was a specific grain size. So we know what we had, but we didn't like mix it and then retest it or anything. We used that specifically, and we used ODOT standard, or we used our standard spec for compost also. Someone asked about the compost eventually decomposing and reducing the benefit of the infiltration. Definitely true. We've thought about that. No matter what happens, if we think we're going to get, 60% runoff reduction or 75% runoff reduction, we're not going to go all the way there. We're going to step it back a little in our credit. We're going to ask Ohio EPA for it to try to take care of some of that. But we realized that we couldn't keep this we can't monitor this is a wildly huge project, looking at 12 sites over the course of 2.5 years. We just don't have the budget to look at them for 5 years. We could come back later, but we realize that we're considering that. And then as time fills, how much of the filter media will clog with fines and have reduced capacity? Definitely, we definitely think there will be some clogging. However, it's going to be so spread out that even in infiltration standpoints, we expect the grassroots to kind of break that up a little bit. So the solids load from roads and that level spread out is so small that that really hasn't been a problem. So we'll keep an eye on it, but outside of that gravel verge, we really don't anticipate that being a big issue. But it's at 11:30. I know we're not supposed to go over, so thank you, Justin, for that presentation, and thank you all the people who presented for session 6, and thank you for everyone who's attended today. Hopefully you learned something, and feel free to reach out to me or any of the presenters with any additional questions. So thank you very much.